Okay, so number one, limit as x approaches 0, root 2 plus x minus root 2 over x. Okay, first things first, direct substitution. So I'll go ahead and show you that step here. Plug in 0 for x, we get root 2 minus root 2, which is 0 over 0. We know there's a hole, but the limit does exist. We have to continue working. We can't leave our answer in this form. Okay, so we go through our conjugate method. Spoil the top, but leave the denominator alone. Okay, we try to combine some like terms. 2 minus 2, that goes away nicely, so that's 0. And we're targeting the hole, trying to find what's causing the hole. We know there's an x that's in the denominator that's part of the cause, but then there's also a x that's hiding in the numerator, and we're here able to find it. There's that x now able to pair up and cancel each other out. There's still a 1 left over in the numerator, so now we're going to reevaluate our limit, replace any remaining x with 0, and that should take us to a number. So 1 root 2 plus 1 root 2 is going to be 2 root 2. You don't have to rationalize the denominator. This is fine. Now, would this problem be any different if I somehow had a one-sided limit up here? Did that change anything? No. Okay. So no decimals, right? We only do decimals if you're getting something that is telling us a vertical asymptote. Otherwise, you can just ignore it. Right? There's no decimals involved unless you know there's a vertical asymptote. Okay, number 2. And it says for x doesn't equal to 4, the function is equal to this function. What should the value be assigned to make the graph continuous? So you see the word continuous. So let's just go down continuity conditions, right? Go down continuity conditions, and then you're going to be able to find your answer. So here's our function. Continuous at x equals 4. Well, our condition says, let's start with the points. We want to find h of 4. And we know that's the unknown, right? We don't know what that is. That's what we're looking for. So we'll leave that empty, and hopefully we can come back to it and figure out what h of 4 must be equal to. Okay, but second condition, the limit. Well, there's only one function, so we're going to evaluate the limit as x approaches 4. All right, first things first, direct substitution. We get 16 plus 4 is 20, 20 minus 20 is 0. So we do get 0 over 0. Continue to work on this, look for the hole. Multiplies to be negative 20, adds up to be 1. 5 and negative 4. Okay, we remove the whole. All right, not approaches 0, approaches 4. Like that. Okay, remove the whole, we reevaluate, we get 4 in for x, 4 plus 5 is 9. Okay, so we have our limit, it passes the test, and we keep going. We're at third condition. In order for a third condition to work, h of 4 must be equal to the limits as x approaches 4 of f of h of x. And in order for this to work, h of 4 must be equal to what? 9. Yeah.
All 3 steps and explaining it out.
Yeah, yeah. So if you just step through continuity condition, anytime the problem says there's the continuity involved, step through your conditions and you'll be able to answer your questions. Okay, number 3. Number 3 says, find the value for constant k that will make the function continuous at x equals 0. So again, you see that statement about continuity. So same thing, we just step through continuity conditions, and before you know it, we'll be able to solve for k just by virtue of our conditions. All right, so first condition, we want to find f of 0. We know that's the target x value. Also, even if it didn't tell you, you knew that 0 is going to be the place that we're going to be focusing our attention on. F of 0, which one do we use? First or second? First one, yep, there's the equal sign there. Okay, so 0 squared minus 2. Right, keep going. All right, we want to evaluate the limit, but to evaluate the limits, do we need 1 or 2 statements? 2 statements. I have something to the left of 0, I have something to the right of 0. They're both defined separately. So we evaluate the limit separately. Make sure you put the notation though. We want to approach 0 from the left side of 0. We want to approach 0 from the right side of 0.
If it's like unequal, instead of like the greater than or equal to, if it's just like equal, an equal sign and then doesn't equal, is it still left and right?
No, it's just one limit condition.
Okay.
And the reason why is because if you see the word doesn't equal to, it means that function is for everything except at -2 or at the other value. The other value is a point. The point has no say on the limit, so you just do one limit statement. Okay, so we do our one-sided limit. We just plug in 0 for both. So here we get 0 minus 2, which is still -2. This side, what do we get? 0 plus k, which is k. Now, in order for the function to be continuous, it's got to pass this test. So what has to happen in order for this to pass the test? Right, the one-sided limits have to be in agreement, right? And before you know it, you solve for k. So k must be equal to -2 in order for our limit to exist. And as soon as you find your answer, you don't have to go any further. I just want you to use continuity condition as a way to set up your problem. That way you have something structured to work from. Okay, we'll skip number 4. Number 5 is kind of like an application of IVT. I think it helps if you just sketch this graph out, right? We know the function is continuous. We have a list of all these ordered pairs, and it says, what is the least number of solutions does the equation f of x equals 1/2 have on the closed interval from 1 to a? So what that means is, how many times can we guarantee that the graph is going to cross a y value of 1/2 based off of these numbers? Okay. So you can do it without graphing it, but visually, I think it's easier if you graph it. So Okay, so y equals 1/2 is here. So I start off at 1, -2. I go up to 2, 3. I come down to 3, 1. I go all the way down to 5, -5, -5, and I go all the way up to 8, 7. So if I have to connect these dots with no breaks in between, what's the least number of times that I can do it? That I can cross that horizontal line, or that y equals 1/2. 3 times, right? So I have to go through it once here. I gotta go through it once here. I gotta go through it once here. 3 places. And the way that you can do this without having to graph is you look at your y values and you ask, okay, how many times does a y value has to cross 1/2? So from -2 to 3, it's got to cross 1/2 in that interval. From 3 to 1, it doesn't have to hit it. From 1 to -5, it has to go past 1/2 to get from 1 to -5. And then from -5 to 7, it's gotta cross 1/2 once at least to get to 7. Okay, 22, we're going to read the graph and see if we can determine. By the way, if you can't see it, there's the graph does extend. Oops, sorry. There is a part of graph right here. It kind of blends into the line there, but the graph does flatten out for a moment there. Hard to see. Okay, limit as x approaches -3 from the left side of -3. So we go to the left side of -3. We see where that arrow is pointing. This arrow is headed towards a positive y value of 3. Approaching 1 from the left of -1. So we know it's going to be this portion there that is heading to a y value of 1. Approaching -3 from the right side of -3. So that arrow is headed towards a y value of 3. The full limits, I'm sorry, let's do this one here. Limit as x approaches 1, -1 from the right side of 1. That's headed to a y value of 2. Now we're asking, what is the full limit? In order for a full limit as x equals -3, the one side limit have to agree. So the arrows headed towards the same y value? They are. So they're both headed towards 3. In order for a limit as x approaches -1 to exist, you have to make sure that the arrows are headed to the same y value, and they are not. One arrow is headed towards 1, the other y value is headed towards 2. So this does not exist. Okay, use continuity conditions to justify if the graph is continuous at x equals 1. So we go through our continuity conditions, but we can read it off of the graph here. So we can say, okay, let's start off with f of 1. F of 1 is all the way down here. That's -5. Second statement, limit as x approaches 1 of f of x. Make sure you put f of x here. We can't just say limit as x approaches 1 is equal to, right? Got to have something there to indicate what you're talking about. What's the limit as x approaches 1? 2, right? I pick points on either side of 1. The arrows are headed towards a y value of 2. So limit does exist. It passes the second condition. The third condition says f of 1 has to equal the limit as x approaches 1 of f of x. Okay, is this a true statement? Not a true statement. I'll say it doesn't equal to, so it's going to fail that third condition. Therefore, what type of discontinuity? Removable.
one or more. Like if the right side's equal and the left side's not, then it's still,
Then it's non-removable, right?
but it's not.
It's not, yeah. Non-removable is what the second condition fails. If the third condition fails, it's a removable discontinuity.
Oh, I think it's just non,
Oh,
no.
let me see.
no.
Like for the word document as failed.
Yeah, on my key, I have removable discontinuity. Right?
So you pass.
Yes, okay, so. Yeah, let me go through those steps. I have on page 9 a summary sheet here. Page 9. Okay, so the first condition is, does the point exist? The second condition is, does the limit exist? Sometimes we got to do one side limit. Third condition is saying, does the point live where the limit lives? Okay, if function passes all three conditions, the function has continuity at x equals c. If condition 2 fails, that means the limit doesn't exist. And if the limit doesn't exist, that means we have a non-removable discontinuity at x equals c. If the second condition passes, but then fails the third condition, that means the function has a removable discontinuity at x equals c.
So like basically if one is equal to the, if like the right side's equal to the first one, that's removable.
In order for it to be removable, it's got to pass the second one and fail the third one. Yeah. So a non-removable looks like this, where the graph is obviously disconnected, right? That's non-removable. Removable is where there's a hole, and then the point is either undefined or is living elsewhere, right? So this is removable. This is non-removable.
We get 4 times to use test rate. No match us today.
Yeah.
Okay.
Let's specify though. We want to specify it's removable discontinuity at x equals 1. Seven, find the value of k that makes f of x continuous. So again, I see the word continuous. I'm just going to walk through continuity conditions and I'm going to be able to solve for k just by going through my steps. Okay, so first step, I want to find f of -3. Sorry, g of -3. What's g of -3? Just k, right? We don't know what k is yet, but we're just gathering information right now. Second condition, I want to evaluate the limit. Do I need 2 limit statement or can I just get away with 1? Or just 1, that's right. The function is up here. This is just a point. A point has no say on what the limit is, so we don't have to do anything with one side limit here. All the graph is, I mean, you can do one side limit, but then you're doing one side limit for the same function and that's overkill, right? There's no need to do one side limit if you're talking about the same graph on both sides. Okay, so first things first, we go through direct substitution. 0 over 0, so we know limit exists. We go through factoring, multiplies to be -6, adds up to be 1. We find what's causing the hole, we remove it. Reevaluate, and we get what?
-5.
Yeah, -5. All right, and now the third, we keep going, right? We haven't solved for k yet, but the third condition says in order for a third condition to pass, my order pair has to live where the limit is. So it says continuous, so it's got to pass through all three conditions. So in order for this to be true, what has to happen?
My intermediate value.
Yeah, k has to be equal to
Oh.
what? -5. And once we solve for k, we can stop.
Also, it's not even about like it's about finding the value. It's not even about like the law itself, like that, or the theorem.
Well, we're trying to figure out what k value can we set to be a number that will allow everything to work out, right? Where the point is going to live, is going to fill in that hole, and my k is -5, then that hole that's created with the second condition is going to be filled in with that point.
But is this an intermediate value theorem? Though?
No, we'll come through that later. Intermediate value theorem is where there's a lower value and a higher value. You're trying to figure out if that middle y value is going to be reached.
Yeah.
But I mean, if you see anything with continuity, that's, it says what will make the function continuous. This is going to be continuity condition.
Oh, so the first condition is finding a point. The second one's finding the limit,
That's right.
and the third one's same or equal.
There you go.
Okay.
When they're done with all of this, are we on horizontal ones?
Yeah, I'll do one of those. Yeah.
What?
Okay, number 8. We're just going to treat these like two separate problems, and we're just going to approach it that way. So here's number 8. Okay, so we're just going to find the limit as x approaches 3 from the right. Okay, so again, it says it's just basically two separate problems. We're just going to find them separately, and then we'll match our answers. So let's go through our steps here. What's the first thing we do if we see
Plug in 3.
Plug in 3. Okay. What do we get?
You get 12 to 0.
This is very telling, right? This is important for us to know what this means. What does this mean here?
Does not exist.
Because there's a what?
Vertical
asymptote. Usually the limit doesn't exist, but it's a one-side limit. So I want to kind of, you don't have to draw this, but I want to just have I think it helps if students have an idea what's happening, right? So there's a vertical asymptote. You know that you're approaching an asymptote. So if you're approaching an asymptote, what's going to happen? Either it's going to go
up all the way
up,
down,
or it's going to go down, right? It's not both, right? It can't be both, otherwise it's not a function. So we're choosing between these two options because we don't know which one it is, and we want to choose it.
like in 100.
Well, is 100 going to be the way we do this? We want to get closer towards 3, right? 100 is going to be over here. That's not going to help us figure out the behavior. We want to pick a value close to 3 I'm sorry, this is plus, right? I bet. 3 from the right, so yeah. So the graph is doing this. It's coming, we're trying to figure out from coming up from the right side, is it approaching positive or negative infinity? And you want to choose a value that's close to 3 on the right side of 3. So we'll test 3.1. Okay, so 3.1 in for x. Don't really care about the numeric value. We just care about what the signs are. So the numerator, we get positive. Denominator, we get positive. Positive over positive is positive.
Wait, isn't the denominator negative? It's 3 minus 3.1.
Oh, right. So that should be negative. Yeah.
You ready for this?
Okay, that's the first part. The part B here. Limit as x approaches infinity. Now, what do we do when we see infinity?
Plug in 100. No.
I mean, there is a time when we plug in 100, but what do we need to figure out first before we do anything? Compare degrees, right? So if it's a real number, you plug in the real number. If it's infinity, you're going to compare degrees. Okay. And then if we get a certain result, then we can decide, okay, is there a horizontal asymptote, or do we need to plug in like 100 or negative 100? But we don't want plugging in to be the first thing, right? Is comparing degrees. Now, is it easy to compare degrees right now?
Yeah.
What can we do to make it easier? Yeah, FOIL out. Now, I mean, you can FOIL everything out, but really the only value that we care about is the what? The highest degree, right? So, I mean, you can FOIL everything out, but really it's just whatever causes the highest degree. Everything, any of the lower degrees is not going to matter. So if I FOIL this out, my highest degree is going to be x to the fourth, and my coefficient is going to be 3x to the fourth. Now, if you want to get everything out, you can, just so that you can have peace of mind that you've looked at everything. So limit as x approaches infinity. Now it's a little bit clearer to see what's going on. What do you notice?
Same.
Same. So if the degrees are the same, how do we find the limit?
Coefficients.
Coefficients. So 3/1 is equal to 3. Now, the 3 is the limit, but it also represents the horizontal asymptote. Visually, what this is saying is that as the graph exits from view, it's going to flatten out around that line y equals 3.
So it can be the limit and the horizontal at the same time.
Yeah, they're the same. They're one and the same. Yeah. Limit as x approaches infinity equals 3 is the same thing as a horizontal asymptote of the function equal to 3. It just means that as you exit, that arrow is going to flatten out at 3. And if it flattens out at 3, that is where your horizontal asymptote is.
And you said when you graph a horizontal asymptote, you can like cross it, right? Presumably.
You can cross it, yeah. So if I do a dotted line, I like to do a dotted line outside the graph, so I don't look at that dotted line in the middle and feel restricted that I can't cross that line. But yeah, you can cross a horizontal asymptote. You just can't cross a vertical asymptote. Okay. Now let me do something a little bit related here. What if I had this? What if I had that? Oh, let's see.
Then you plug in 100.
Well, but first we
Yeah.
we do what?
Look at it.
Look at the the degree of the exponents, and what do you notice here?
The top one.
Top one is higher, which means that this fraction is doing what?
It's
Increasing.
Increasing. It's either going in this direction or this direction. So remember, you only plug in a value like 100 or large number, or you'd only deal with decimals or 100 if you realize that you're trying to choose between two options, right? You're only doing that test because you're down to two options and you're trying to figure it out. That's not the first step, right? First step is figuring out which category you're in. And then once you're sure of the category and you realize that, okay, I still have a decision to make, then you can worry about plugging the value. So here, what can I insert into the test?
100.
So if I plug 100 into the numerator, I get positive. If I plug 100 into the denominator, I get negative. So positive over negative is negative.
And if the denominator degree is bigger and it's 0.
It's just 0, right? So I'll do an example of that. If its limit as x approaches negative infinity, it's approaching infinity or negative infinity, we compare degrees, the higher degrees in the denominator. So that's going to lead us to 0. But I do see this, too many times students want to jump to this conclusion without first deciding which category you're in, right? You want to decide which category you're in before you're committing to testing. All right, so let's look at number 9 here. Evaluating limits as x approaches 0. So first things first, we plug in 0. 3 minus root 9 is 0. 0 over 0. We know there's a hole.
Conjugate.
Right, so we clean up the top, but we leave the denominator alone. So 3 times 3 is 9. 9 minus, now this becomes x plus 9, but there's something we gotta be careful about. Okay, what about the negative?
Oh, breaths.
Parentheses. Because if we leave out the parentheses, we're gonna end up doing 9 plus 9, which is not the case, right? That negative is gonna distribute through the parentheses, so even though the radical drops out, the negative is going to end up impacting everything that comes after it. Okay, combine all your like terms in the numerator. Okay, what happens up top? 9 minus 9 is 0, that goes away.
That's probably.
Good, x's cancel out, but we got to keep track of the fact that there's still that negative sitting there. So there's a -1 that's going to still be in front. But at least the whole is gone. We can reevaluate. We should get down to a real number here.
Also, even after like square root goes away, it still stays as like one within the parentheses.
I'm sorry.
Even after the square root goes away for x plus 9, it still stays in.
That's right. Still have, well, the reason why is because there's a minus in front. Now, if this is a plus, then I will drop the parentheses. I don't care. But if there's a negative and there's multiple terms that come after it, I like to use the parentheses. Otherwise, I feel like I'm going to forget about distributing.
Yeah, because I forgot to. I wouldn't have known to change 9 to negative. It's.
Yeah. We want to make sure that it's always safest, especially if you can see a negative, to distribute that negative through. Okay, so now root 9 is 3. So 3 plus 3 is 6. Okay, let's practice sketching our graph here. Okay, so I'm going to just go from A through J here. Limit as x approaches negative infinity equals negative infinity. What does this tell us? What's happening here?
I mean,
As approaching the left side.
Okay.
Of the graph, it's going to negative infinity.
Yep, so this is telling us that as my arrow exits from view towards the left, that arrow is going to point down.
still horizontal.
No horizontal. If this is horizontal, this will be equal to a number. But this arrow is basically going down like that. Right. If it was negative, if it's approaching infinity is equal to a number, then that arrow will flatten out. But remember, anything that comes on this side is talking about the behavior of the y value. This is talking about the movement of the x value.
Can you draw outside the graph?
Yeah, I like it outside the graph, so it's outside of view, so it doesn't get. Yeah, that's my preference. I mean, you can put it inside if you want, but I don't want to conflict with the rest of this graph here. Okay, approaching -4 from the left side of -4. The limit is -3. So I like to put a hole there. That's my preference. That's where I can. Want to just do a slight extension there, but I don't want to go too far. Okay, limit as x approaches -4 from the right side of -4 is equal to 1. Right, everybody good so far? All right, limit, let's see, h of 6 is undefined, so that just tells me, okay, I just want to make sure at the end of the problem, I don't have anything defined as 6. There's nothing I can put there because
It's not a vertical asymptote. You just like leave it.
it could be, but right now I'm not going to put anything there. It just means that the point is undefined. Could be a vertical asymptote, could be a hole, but I don't want to put anything there if nothing's there already. It's already fulfilling my condition. Okay, approaching 0 from the left side of 0 is -infinity. So what's happening here?
That's a vertical asymptote.
Asymptote, but just from, but the graph, this is only describing the graph from which side?
Left side.
From the left side here. So when my arrow is going down, I like to put it down here. If it's going up, I like to put it up here. It just feels a little bit more, doesn't feel as messy. So I'm going to put just a slight arrow here. If I wanted to, I could connect this if I wanted to. Don't have to. Okay, but then the limit as x approaches 0 does not exist, so, I don't, yeah. So, I mean, I could do anything here. I can leave this empty. I could go down, I can go up. Either way, we already know there's vertical asymptote, so limit doesn't exist. That's perfectly fine. We leave it the way it is. Okay, approaching 3 from the right is -4. Approaching 4 is -infinity, so what does this tell us? Vertical asymptote. And anything special about this? Both, yeah, both branches are going to go down. Limit as approaches 6 equals 3. This is a full limit. So a full limit, that means I want, I'll put a hole there and I'm going to extend from the hole from both sides. Limit as x approaches positive infinity equals -2. So what is this telling us? Horizontal asymptote, right? So I'm gonna draw my arrow off the grid, and that arrow is gonna flatten out at -2.
Is there any one way to like identify the point, like graphs on a point already drawn and we did, that's like it.
Yeah, we can do one of those. Okay, let me do some more problems that was not on the worksheet. If you guys want to grab a sheet of paper, or you can grab one of my scratch sheets from my shelf. This is a IVT problem from scratch. Okay, verify that IVT applies. So we have our function, we have our closed interval, we have our targets. Okay, first things first, we have to confirm that the function is what? Continuous. Do you see any variable in the denominator? No, this is a polynomial. So polynomial is safe, it's continuous everywhere.
How do you know it's continuous?
Because there's no variable in the denominator.
Oh,
That means there's no hole, there's no asymptote. Right, everything is up here. And the nice thing about a polynomial is that it's a nice smooth curve. There's not going to be any breaks in the graph. Okay, so we know that there's no surprises with the graph. There's not going to be a sudden jump or a sudden place where the graph is undefined. We want to target, we know our goal is 10, y value of 10. So that means we want one of these y values to be below 10 and the other to be what? Above 10. But remember, these are x values. So we don't want to say, oh, 10 is outside of 0 to 7. So it doesn't work, right? You're not comparing the same things here. So we got to find the y values from these x value intervals. So let's find f of 0. F of 0 gives us 7. All right, so if we're starting at a y value of 7, and we go all the way up to y value of 70, and there's no breaks in between, am I guaranteed to hit a y value of 10 somewhere in between?
Yes.
Yes, right. So IVT is a guarantee, so we have to make a statement about that. So we say by IVT, since my lower point is at 7, I'll say it's coming from one of my endpoints, f of 0 equals 7 is less than 10, and 10 is sitting nicely between 7 and 70, and 70 is coming from my other endpoint. I know that there must be a y value of 10 somewhere on the interval from 0 to 10.
Also, like, and this for a degree in lesson science, you do it like opposite, where it says 70 equals f7. You do it like,
Yeah, you can.
It doesn't really matter.
Yeah, if you want to flip f7 is equal to 7, you can do that as well. It's just, I put these next to each other. It makes it easier for me to compare that. Okay, 10 is obviously between 7 and 70. All right, so now the next step is find the C value. So C value, we have to figure out the X value where this graph is actually going to hit 10. So what do we do? How do we get there? Plug 10 in for the Y, right? The 10 is going to go in for the Y, and we're going to solve for X. Okay, bring everything over to one side. So there I have A times C here. So multiplies to be -6, adds up to be -5. So that's going to be -6 and 1, right? Multiplies to be -6, adds up to be -5. But I got to worry about that coefficient in front, so I got to divide by 2 here. If I can't divide out, I'm going to pull that denominator out in front. Solve for X, I get X equals 3 and -1/2.
that's okay, right? Because it goes.
Well, these are X values.
Oh, okay.
These are X values. So there's two places where the graph is actually going to hit 10. These are the two ordered pairs, 3, 10 and -1/2, 10. But are both of these in the interval that we care about?
Oh, no.
No, we only care from 0 to 7. So which one is out?
-1/2,
That 1/2, that's out.
Can you do a number of continuity?
I'm sorry.
Can you do number continuity conditions?
I think we did a couple of those already, but I can go through with it after it helps us.
Okay.
Let's do one where there's a horizontal asymptote, but with a strange condition here. So let's number 11 here. Oh yeah, that's it. Find the horizontal asymptotes for okay. Anytime we want to find the horizontal asymptote, that's the same thing as doing what? Finding the limit as x approaches what? Infinity and -infinity, right? And what do you notice about this problem that's a little bit strange in terms of asymptotes? Square root, which means that there's potentially what? How many asymptotes? Two, right? There could be that split asymptote going on. So let's see if we can. We'll go through one at a time and. All right, so if we know that we're approaching infinity, what's our first step?
Check the degree.
Check the degrees. Yeah. Okay. So what's the degree of my numerator?
The same as the denominator.
Degree is 1, right? Denominator is also a 1. So my degrees are the same, then my limit is just the what?
Coefficients.
Ratio of the coefficient. What's the coefficient of this one here? 1. So 1 over -5. So there's one asymptote. But what if I went the other direction? same problem. I compare degrees again, I'm gonna get the same result. But let's test 100 here, or let's, what number can we test? Sorry, what number can we test? Negative 100. So if I insert negative 100 in for x, what's gonna happen here? Will it be positive or be negative?
Pretty positive.
Positive, because if I do negative 100 squared, that's a positive value, and that's bigger than this one, so that's positive. But if I insert negative 100 in for the denominator, I get positive. So positive over positive is positive. So I'm going to have two asymptotes. The good thing is that they both are virtually this. I mean, they're the same numeric value, they're just different signs. So if I want to find the horizontal asymptote, I'll say my horizontal asymptotes are at y equals negative 1/5 and y is equal to 1.
Sort of opposites.
Yeah, different signs. Yeah. So the graph may look something like this, where, you know, from one side is negative 1/5, the other side is positive 1/5. You don't have to draw the graph. I just want to just show you why we have two answers.
For like the L.
Yeah, so I'll do one of those as well.
What's like the speed of the graph?
So if I have different families of function between numerator and denominator, I can see which one is growing faster, and then I can decide whether it's going to go to 0 or infinity. So in this case, this, let me change that bit. So as a reminder, logs move the slowest, followed by radicals, followed by polynomials, followed by exponentials. So here, what category can I place this in?
Radicals.
Radical. Okay, so radicals up top. Logs. Okay, which is growing at a faster rate,
Top
which means that this fraction is getting what?
larger.
Larger. So we have two options, right? Either positive infinity or negative infinity. Right, so what can we test?
100 and negative.
Well, it's only approaching
Oh yeah.
infinity, so only 100. So if I plug 100 into the numerator, I get positive. If I plug 100 into the denominator, I get
Negative.
negative. Yeah, there's a negative in front, right? No matter how big the number is, there's still that negative in front. So positive over negative is negative. Okay, let me do one more of these so you can see all the different variations.
Early two or very few.
There's 4: logs, radicals, polynomials, and exponentials.
If we call this one the same. so-
They won't be the same because they'll be in different families of functions. They're all going to fall in different categories.
So you're never gonna have like two logs of each other.
Right, no, I'm not gonna do that, yeah. If this comparative growth rates, it's gotta be different. Otherwise, you know, we won't be able to know. Okay, limit as x approaches infinity, we have different families of functions above and below. The numerator falls under what category?
Polynomials.
The denominator is
Exponential.
exponential. Which one is growing faster?
Bottom.
Exponential. So what's gonna happen to this fraction?
Think of the 0.
Yeah, getting closer towards 0.
It's always gonna be 0 like numerator.
Right, yep. It's either 0 or plus or minus infinity. The top is growing faster, it's always getting larger. Bottom is getting faster, then it's gonna be,
It's like that for horizontal asymptote too. Whenever the denominator is bigger than the numerator.
yeah, it's always 0, right?
Thank you.
Okay, appreciate it, thanks. All right, I'll walk around, see if you guys have any individual questions for me.
How do you do this one?
Yesterday I thought it was so right. Now I think. Differentiate between two different conditions.
Here,
The continuity condition is something. Yeah. The process is easy. It's a very process. Yeah.
well, if you don't have a hundred thing, the approach infinity and the three higher.
Yeah. Else, part of the very first thing you learned was like the points where it's drawn on the graph, you need to figure out what it was. Yeah. I feel like that's good hard for me to do.
I sketched the graph out.
Yeah. We've done that.
So scared.
I watched the video. I was like. What about you? What sort of thing?
It's saying, how many times is my graph here, you get the y value one half? So I plotted all these points, we got 8 rings, I plotted all these points. And here's my 1/2, and I just decided, okay, the only way to connect all these dots.
Wait.
I mean, I know these are stuff, that I can get that y value 1/2. Yeah, but after this one, right. Yeah, that's fine.
So.
That's like, I didn't talk that.
So the only difference in approach for like continuity, if it was like greater than less than, we used to do 2 limits. The only difference. Or solve for both sides of the limit.
Yeah, so if you see it doesn't equal 2 and equal 2, then you're only gonna do the limit one time. If you see less than greater than, then you'll do one side limit.
Okay. But then how do you know what the coordinate is if it's less than or greater than?
You use the equal sign. The equal sign is telling you that f of 3 is the top function. Right, less than or equal to.
Oh, okay. So it's equal to like the, you plug in the 3 for like the.
It's a for the x of the top one, yeah.
Okay, all right, thank you. You ready for this test?
So,
Yeah.
approaching
Yesterday I thought I was like really ready and it's like, today, I don't know.
So which one of these is
I would
approaching
do
negative
it every single note.
Yeah.
Every single person.
But this.
I struggle with like the, difference between the, I do iterate conditions and then make target.
Again, so what do you think? What if I tell you? Right, so there's a part of classroom, so I know my loop doesn't exist. We get going to the left side of -4. I think now I can do the best one. If I'm deciding, you can see there plus or minus this. Yeah, one to the numerator to denominator, and if I get a positive or a negative, or negative or positive, I decide what gets your side of the
How do you know, like, when it's like both of them, or do you think one?
Oh, it's always the one. Yeah, I won't answer that. Unless the problem asks you specifically. Just a negative.
Okay.
Yeah, don't drop the vote.
Alright. And it's just like 4 positive, then we just do 4 for 1.
-4 for the right side of the floor is negative. Really on
Like,
side.
it's like a positive, but that's the reason.
Well, it's different. If it's on the positive negative side. If its limit as x approaches -4 from the right side of -4. If you look at your number line here, negative is a little bit different. Here's -4, here's -5, here's -3. From the right side of -4, I gotta pick a number on this side, so it's gonna be -3. If it's -4 from the left side -4, then I choose -3.
There.
But it's opposite if it was like 4, 3, and 5. Like the left side is going to be 3, 4, the right side is going to be 4.
I just need to
know
know
that
that.
Signs are, negative side is a little bit different, so just draw a number line, right? So which side is the negative side.
So there's gonna be questions from like the quiz. That's too.
Yeah. Yeah, if you look at the last page, it has all the, identify all the types of problems you're going to see in all the times. That's right. Yeah, I brought the x up as 1 over x, and that can really help me see that they cancel out. And once they cancel out, you can.
Oh, I don't know. Oh, wait, no, we're okay.
Oh, can you do a common denominator one?
Yeah.
It's like saying it like five things that you said.
Yeah, so once you cancel stuff out, you're always reevaluating to get to your limit. I made you look at a more specific example. Yeah, so I'm just going through conditions here, seeing if it's continuous or not. So if I plug in f of 3, that's, I use the first expression. If in order for a limit to exist, I got to one side limit, the limit the limit of function 3 from the left, function 2 from the right. I see that these are not the same, so my limit doesn't exist because they're not in agreement, so therefore not. You have your quiz on me?
How many words?
No, no. Guys, eventually I need all your book bags up in the front.
I do my quiz.
Yeah, we'll do that. We'll do that.
Oh, if you're. You like bring X over like 1 over X. Yeah. Put our bags in the front.
Yeah, fascinating.
You know your input
Yeah.
test?
Can you sign and put my grade here?
Yeah.
Thank you.
I'll bring it to you.
Okay. So you don't need to do now.
Okay, okay.
We're done the concert.
Sure.
Yesterday I thought I was ready today, I don't know. Yeah, I was here for 7:30. I was watching it. I was ready yesterday, today, I don't know. So we can find help. Yes. It's a good thing, I mean, probably.
So you said it when you evaluation. So it's like.
Like yesterday, I was right today, I don't know.
Then you can do the same thing. Specific for stuff. That's how.
Is there anything that I can do?
Yeah.
Well, yeah, it would be like an on.
So, over on your brightness, some programs.
Okay, those are just.
Yeah.
Like guys.
I guess. Yeah, that's, this one. Okay, it's the constants, okay.
Yeah.
Flavors.
Guys, if you feel like you need a scratch sheet, you can always grab one. your test will go in the folder, which is next to your thoughts.